so we're back again. Before we move on and take a look at the next example, don't be too distracted by this amazing picture that I've drawn. We'll get there in a second, I promise. I did want to take a moment and point out something about this four-step optimization procedure. It's really important to make sure that you actually get that first step right. Most mistakes I end up seeing when it comes to this, when I look at student work on optimization problems, is misidentifying that objective function at the very beginning. And the best case scenario, they figure out something has gone wrong and they go back to the drawing board. Worst case scenario, they start making more mistakes in an attempt to make what they've done fit together, and it either gets really, really awful or they just end up throwing in the towel. So I cannot stress enough how important it is to make sure you identify your objective function correctly. Failing to do so is going to lead to wailing and gnashing of teeth. Moving on, I wanted to take a look at the not quite the next example. So there's a couple in there that I'm going to leave for you to work on, exercises for the student, if you will. But I did want to take a look at the last couple of examples attached to the four-step procedure because they're a bit more intricate in terms of how they set things up, and I find that it's a bit less likely that students remember all of the bits and pieces they need in order to make these guys work. So, flush with our success from working with the farmer on his fence, we've been hired by a soup company or a tuna company, somebody who puts something in cans. So they want us to make a can. I'm probably going to keep going with soup, but whatever. So we know that soup cans look like cylinders, thus the picture here. So we know they want us to enclose 16 pi cubic inches worth of soup. It's really specific, but hey, they're writing our paychecks, so let's just go with it. So the objective is, in this case, we want to use as little metal as possible in closing the 16 pi cubic inches worth of stuff. So that's going to drive what we're doing going forward. First order of business using our optimization procedure, we need to identify our objective function. Making this thing as cheaply as possible means using a minimum of metal in the can. So that means we really want to minimize the surface area of this thing, which can be a bit daunting to try to figure out how to process. So we want a minimum instead of a maximum this time. That's going to be significant as we go forward. I'm going to call my surface area S. Now, what this ends up breaking down as, and where I said it's a little more complicated than what we dealt with in the last example where we had a rectangle that we were working with, is figuring out how to compute the surface area of this thing. You may remember the formula from a geometry class. If so, fantastic. If not, it's okay, I get it. The idea is we've got a top and a bottom. They're each circles. So each of those would have an area of pi times the radius squared, which I've labeled as r here. So we have two of them. So we have 2 pi r squared. We also have the side piece, which at the moment is going to, if you take off the top and the bottom, it's like a metal, tube. So we've got 2 pi times r times h ends up being the area of that thing. Now I'm leaving it for you to determine exactly how I go from taking this cylindrical tube and tell you that that's the area that ends up coming out of it. That is an exercise for you to tackle. Anyway, like we've seen before, we have an objective function. It's got 2 variables in it. This probably isn't surprising at this stage. We've seen 2 variables pop up in all of our examples so far. So now, step 2 of the process says, find a way to take this thing and make it a 1 variable objective function that we can do our standard Calc 1 tricks on. We've been told that we need to enclose 16 pi cubic inches worth of soup. So that is a volume value. So we know that our volume needs to be 16 pi. Now, real quick, if you know the volume of how to calculate the volume of a cylinder, awesome. If not, the formula looks like this. Pi times the radius squared times the height. Basically, base area is a circle times the height. That gives you the volume of the cylinder. So, unlike our previous examples, again, technically you could solve for either of these 2 variables, but this time around I'm going to make an executive decision. It is way easier to get h by itself because isolating r requires a square root, and we don't want to have to deal with that if we can avoid it, right? So, pi picture. So, to get h by itself, we divide both sides of our equation by this pi r squared. Shock and dismay, the pi's cancel, and that leaves us with 16r to the negative second. Like I said, I'm going to convert this into a negative exponent because it makes the calculus easier when we get to step 3. So the first part of our objective function doesn't change. It's still 2 pi r squared. Where it does change is instead of having h here, we feed in the formula that we just came up with. So that's 2 pi r times 16r to the negative second. A little algebraic razzmatazz, and we've got 2 pi r squared, that is a plus, 32 pi r to the minus first. So now, single variable objective function, step 2 accomplished. Now we can do calculus stuff with it. We're done building things up, so to speak. So we track down critical numbers. So critical numbers require us to calculate a derivative. So S prime of r, executing our power rule this time around. First guy, 2 hops out front, exponent goes down by 1. We've got 4 pi r there. Here, the negative 1 hops out front, so we have negative 32 pi r to the negative second. Like with our very first example, this is undefined when r is 0, but we aren't going to be telling our bosses, don't make a can at all. That, isn't going to get us a good paycheck. So we take this thing, we set it equal to 0, and now we solve for r. I'm short on board space, as you can tell. Pikachu keeps telling me about it. So I'm going to hop over some of the algebra here. Maneuvering this thing around is going to end up giving us So what I did was I added this term over to the other side and then multiplied both sides of my equation by r squared. So r to the negative second times r to the positive second, they vanish in a public logic. Over here, I've got r times r squared, thus 4 pi r cubed equals 32 pi. So now from here, it's not too tough to get r by itself. We divide both sides by 4 pi. Again, shock and dismay. Pi's cancel. 32 divided by 4 is 8. So the last thing we need to do to get r by itself is calculate a cube root, and so we have an r value of 2 inches. Awesome. As we've seen previously, our bosses probably aren't going to be too happy if we just stop and say, r is 2. Pay me, please. That's not going to end well for either us or our bosses. So we need to answer the actual question, determine the dimensions of the can that they should set up their manufacturing system to put up for them. We also do want to make sure that we are in fact minimizing the amount of metal we use. So we have 0 acting as a real world cutoff for what we're doing. Our candidate is 2. If we plug r equals 1, again, 1 is sitting here and it's super easy to work with. We have 4 pi minus 32 pi. That is very negative. So once we move past 2, again, I like going with a million. 32 pi divided by a million squared is really tiny. So 4 pi r, I was going to say 4 pi times a million minus something that's small, And that is doing what we wanted. We're dropping, we flatten out, we start climbing again. That indicates that we have hit a minimum. Sweet. So our minimum radius is going to be 2 inches. And we've worked out previously where we're going to end up getting our h. It was 16 divided by r squared. I wrote it as 16r to the minus second, but same principle. So 16 divided by 2 squared. 2 squared is 4. 16 divided by 4 gives us 4 inches. So I don't know if this is why Progresso soup cans are a little more squat than like Campbell's soup cans, but yeah, because our diameter and our height are basically going to be the same now, since the diameter of the circle is twice its radius. So congratulations, another paycheck earned as an optimization consultant. I've got one more example I want to take a look at. Again, we're leaning back into pure math territory versus something you'd seen in application, but it does end up posing one last wrinkle in terms of how we might want to handle these things.